This is the last lecture in equilibrium thermodynamics. Hold your applause. We're going to talk here in this part of lecture 14, the ion activity coefficients. Okay, so chemical potential of ions in solution. Well, for instance, if you dissolve sodium chloride into water, you get ions, and we saw from the last lecture that we have to consider not only the chemical potential but also the electric potential of the sodium ions and chloride ions, and we combine those into an electrochemical potential. Now what we're going to do is to look in more detail about those. And it turns out that these ions are very far from ideal when they're in solution. We might expect that because we have interactions between the ions, and typically we use aqueous solutions, so the ion will interact with the water with ion dipole forces, and therefore considerably altering their behavior from ideal behavior. All right, so actually let's just go and take an example. Suppose we have sodium Na2SO4, sodium sulfate, and we put this in water. What will happen is that we'll get two sodium ions, aqueous, and one sulfate ion, aqueous. All right, so these are the ions in solution that we're interested in. Let's write down the chemical potentials of these. Well, the electrochemical potential of the sodium ions, we have to use electrochemical potential because we're using ions, charges. Well, that will be the standard state electrochemical potential of the sodium ion plus RT times the natural log of the activity of the sodium ions in solution. And where, remember, the activity here, we're going to define as the activity coefficient, taking into account non-ideal behavior, and we're going to use, instead of mole fraction, we're going to use what everybody else uses as molal concentrations. So this will be the molal concentration of sodium ion divided by the standard state, which is 1 molal. So what we're doing here is using a 1 molal standard state. So this, this would be standard state. So this standard state refers to a 1 molal solution. Effectively, that means that we're going to have to express concentrations of ions in molal, and that's what everybody does. If we look at the electrochemical potential of the sulfate, that's the same kind of expression, electrochemical potential of sulfate in the standard state, which is 1 molal, plus RT times the natural log of the activity of sulfate, where the activity of sulfate is the activity coefficient of sulfate times the molal concentration of sulfate divided by the standard state, which is 1 molal concentration. All right, so far so good, but the problem is here that you cannot just measure the chemical potential or electrochemical potential of sodium alone or of sulfate alone, because you can't get a bottle or a solution of just sulfate ions. With the sulfate ions have to come, or with the sulfate ions have to come sodium ions, and vice versa. So really you can't just measure these activity coefficients separately. What you have to do is to look at some combination of the two. Well, let's now look, say, at the total. So the total, we'll have to put in some averages, and we'll define how those averages are in just a minute. But we'll look at the total chemical potential, electrochemical potential. That will be the number of the number of ions of sodium times the chemical potential, this electrochemical potential of the sodium ions, plus the number of sulfate ions times the chemical potential of the sulfate. So total chemical potential of the solutes, which are the sodium ions and the sulfate ions. And here the number of sodium ions you get, ignore my phone, the number of sodium ions you get, the number of sulfate ions you get, is related to the stoichiometric coefficients. Here, the number of sodium ions would be 2, and the number of sulfate ions would just be 1. Okay, so that's the key point, is you can't measure just by itself the sodium ions or the sulfate ions. You have to measure them together and you get some sort of average. Okay, so we know the usual electrochemical potential is the standard state electrochemical potential is RT times the logarithm of activity. And here we're going to express activity as a ratio of concentrations, and the concentration we're going to use is molal. And so therefore we can write the chemical potential as the chemical potential standard state plus RT times the natural log of that. So did we do that? Yes, we did, right there. So there's activity. Okay, let's make a few more points here. The activity coefficient goes to 1 as the molal concentration, or any concentration, goes to 0. So the limit of the activity coefficient goes to 1 as the concentration goes to 0. And that's sort of to be expected. The reason why you have non-ideal behavior, in other words, why we have gamma not equal to 1, is that you have solute-solute and solute solvent interactions. But if you start decreasing the concentration, and in fact as a limit as you go to 0, then the activity coefficient will go to 1 and it'll become ideal because you just have one solute in there. For electrolytes, for ions in solution, the activity coefficient will be less than 1 because of solute-solute and solute-solvent interactions. So there are two. So gamma is less than 1 for two reasons. First of all, you have ion dipole interactions of these ions in water. So for example, you have the sodium ions, then oxygen of the water is partial negative charge, and then you have this ion dipole, and so on. Similarly for the, say, sulfate, you would have the partial positive charge of the oxygen associating with the negative charge in the sulfate. So what this does is it takes out of solution some of the sodium ions. The sodium ions now are bound up by water, and so they're not as active as you expect them to be, and therefore the activity coefficient will be less than 1. And the second reason why the activity coefficient would be less than 1 for ions in solution, ions in water, are a phenomenon called ion pairing. So actually the sodium ions in solution are paired up with the sulfate ions in solution. So you have this ion pairing here, which means that these sodium and sulfate ions are less active because they're not by themselves, they're paired up, and therefore the activity coefficient would be less than 1. Okay, and as we mentioned, we cannot separate positive from negative species in electrolytes, so you have to consider the total electrochemical potential, both the positive and the negative. All right, well, here's an example for sodium chloride. We have the total sodium chloride chemical potential is the sodium standard state plus RT times the activity of sodium plus the chloride standard state plus RT log chloride activity of chloride. For sodium sulfate, the total chemical potential will be, oh, look, you have 2. This is multiplied by 2 because when you put this in water, you get 2 sodium ions, so that's where that 2 comes from. And then you have here the sulfate. All right, so let's continue to develop this idea. And let's take, say a general system where you have N plus, that's the number of ions in solution with positive charge. And let's say N minus will be associated with the number of ions in solution with negative charge. And as I write this, I realize, duh, ions with positive charge are cations. Forgot that. And the negative ions would be anions. So for example, if we have Na2SO4 2 minus, here N plus will be equal to 2, and N minus will be equal to 1. You have only one sulfate, but 2 sodiums when you put it in water. So let's write the total chemical potential of a solution that contains N plus and N minus. The total chemical potential will be the number of species with the plus times the chemical potential, electrochemical potential. Got to remember we have ions of the plus species, plus the number in the minus times the electrochemical potential of the minus species. And again, the plus and minus refer to the stoichiometric coefficients when you dissolve a substance in water. Like for instance, if you have Na2SO4, when you put this in water, you get 2 Na plus and 1 SO4, 2 minus. So the N plus here would be 2, and the N minus here would be 1. All right, so let's go ahead and expand out the electrochemical potential in terms of activities. So this would be the N plus times the standard state electrochemical potential, the plus species, plus RT times the natural log of the activity of the plus species, plus the number of the minus species times the electrochemical potential of the minus species, standard state, plus RT times the natural log of the activity of the minus species. Now let's substitute in activities with our concentrations and activity coefficients. So this is then equal to the number of plus times the electrochemical potential, standard state of the plus RT times the natural log. Again, we're going to put gamma of the plus, when doing the plus species, times the molality of the plus divided by the standard state molality. So here our standard state, this 0 refers to 1 molar concentration, plus the number of the negative charged species times their standard state chemical potential, electrochemical potential, plus RT times the natural log of the activity coefficient of the negative species times their molal solution concentration divided by standard state. All right, so this is interesting. There's a total chemical potential, but it's not particularly useful because it has gamma plus and gamma minus. Those are activity coefficients of just the plus and just the minus species, which we can't really measure. We can measure them together, but not separately. So what one does is to introduce some averaged terms, and I'll write those in just a minute. Just let me rewrite this as N plus mu 0 standard state, sorry, that should be the plus, of the standard state, plus N minus mu plus of the standard state, plus, let me pull out an RT, N plus times the natural log of gamma plus M plus over M0, plus N minus times the natural log of gamma 1 gamma minus. This should be gamma plus, gamma minus. Let me get a little more clear here. M minus over M0. And again, these should be superscript to indicate standard state. All right. Okay, so let's make some approximations, or some assumptions about averages. And when we actually work this out, we'll see why we're making these assumptions, or these averages. Let's first define N plus minus, this symbol, to be N plus plus N minus. Let's define gamma plus minus to be equal to gamma of the plus raised to that coefficient n plus, and remember that's the stoichiometric coefficient when you dissolve it. Here n plus would be 2 for sodium sulfate, times gamma minus raised to the n minus power, all this to the power of 1 over n plus minus. This is the sum of the coefficients. Sum of the coefficients here for sodium sulfate will be 2 plus 1 or 3. And let's define similarly m plus minus, the molal concentration plus minus, to be the molal concentration of the plus raised to the n plus power, times the molal concentration of the minus species raised to the n minus power, divided by raised to the power of 1 over n plus minus. So why do we make these funny averages? So now we have like an average activity coefficient with an average molal solution concentration, an average number, or an average number of plus and minus species. Or actually, that's just the sum, not an average. So why do we do this? Well, let us form the equation, let us form the expression gamma plus minus m plus minus divided by m0. And let's take the log of this and multiply by n plus minus. When we actually do this, what we'll find is that we get this term here. If we multiply by RT, we'll get this term in here, which we can then replace this term, we can then replace with this term. So instead of independently having activity coefficients of the plus or minus, we'll have this averaged activity coefficient of the plus or minus. All right, so let's actually go ahead and do this. Let's take the natural log, substitute in here gamma plus minus, m plus minus, and n plus minus. So n plus minus natural log of gamma plus minus m plus minus over m0, that's equal to n plus minus natural log gamma plus minus, remember that was gamma plus raised to the n plus power, gamma minus raised to the n minus power, all raised to the 1 over n plus minus power. Molal concentration was the plus raised to the n plus power, the minus raised to the n minus power, divided by 1 over n plus minus, divided by m. Sorry, that should not be the whole thing, just that thing you're taking the logarithm of should be divided by m0. And again, I keep forgetting to put those superscript m0. All right, so this is equal to n plus minus. This is multiplies as in plus minus. Let's see, so we have this raised to the n plus minus, and this, 1 over n plus minus, this raised to the 1 over n plus minus, so we can take that out of the logarithm, 1 over n plus minus, times the natural log of gamma plus, let me write this, gamma plus, gamma minus, this is raised to the n plus, is raised to the n minus, here we have m raised to the n plus for the plus, m for minus raised to the n minus, all over m0. Look, that cancels out. Oh, how convenient. So what we're left with, let me rewrite this, is natural log of gamma minus raised to the n minus, m minus raised to the n minus, gamma plus raised to the n plus, gamma, m, m plus raised to the n plus power, And note that the logarithm of a product, here we'll just do this as a product, is a sum of the logarithms. All right, so this will just be the natural log of gamma minus m minus raised to the n minus power plus the natural log of gamma plus m plus raised to the n plus power. And that is equal to, take down the n minus natural log, I forgot to carry along the m0. Sorry. Let me carry along the m0. Well, let me just continue this on the next page. So this is equal to n minus natural log of gamma minus m minus over standard state m0 plus n plus natural log of gamma plus m plus over m0. All right, so what have we done here? We've taken the natural log, we took n plus minus times the natural log of this, okay, and we worked it all out and substituted, and we got n minus times that, n plus times that, and lo and behold, look at that, n plus times that, n minus times that. So this can be replaced by n plus minus times the natural log of gamma plus m plus minus. Okay, so isn't that neat? So I'll just rewrite that. So the total, mu total, was n plus mu plus electrochemical potential standard state plus n minus mu minus standard state plus RT. We had n plus natural log of gamma plus m plus over m0 plus n minus natural log of gamma minus m minus over m0. And we said that this term can be replaced by, let's rewrite this stuff here, mu0 should be a plus n minus mu minus standard state plus RT times n plus minus natural log of gamma plus minus m plus minus over m0. Okay, that's kind of neat. So now, or just let me define mu plus minus standard state as defined as n plus mu plus 0 plus n minus mu minus electrochemical potential 0. In other words, this term we're going to replace with this symbol here. So this is equal to mu plus minus 0 plus RT times the natural log of gamma plus minus m plus minus over m0. And I'm going to take this up and raise that to the power n plus minus. And we're going to define this as the average activity A plus minus. So it's the activity not of the plus or not of the minus, but some sort of average A plus minus. So what we end up with is our familiar equation with these new symbols, plus RT times the natural log of the activity plus minus. So you can't measure activity coefficients independently of the pluses and minuses, but you can do some sort of average, and so the total chemical potential is just this averaged here, or summed there, plus this average activity. All right, so that's the whole point of that long exercise, is that even though you can't independently measure activity coefficients with a plus or minus, you can measure averages. Okay, so that's what all this is about. We made those, and here's the bottom line there, the activity. Now, the average activity of the ions in solution is this expression here, where you have an average activity coefficient, which is defined as the activity coefficient of the pluses and minuses separately. All right, so that was the point of that. Let's do some examples and see if we can figure this thing out. What is the mean molality of a 0.1 molar aqueous solution of Na3PO4? Okay, so remember the mean molality, that would be the M plus minus. That's the molality of the plus solution raised to the N plus times the molality of the negatively charged species raised to the N minus, and all this is raised to the 1 over N plus minus. All right, so to figure out what these N's are and M's are, what we have to do is to look at our compound, Na3PO4, put that in water, Na3PO4, solvate that, that's 3 Na plus 1 PO4, 3 minus. So this is N plus. The 1 there is N minus. I guess I'm using subscripts here. N minus. So N plus minus, remember, is defined as N plus N minus. That's equal to 3 plus 1 is 4. The solution concentration of the plus, so initially the total here was 0.1 molal. Oh, look what's happening. The solution concentration here is 0.100 molal. So the M plus is 3 times that, 0.300 molal. And the M minus, well, if you have a 0.1 molal solution of this, you only have a 0.1 molal solution of that. All right, so I think we have everything here that we need to calculate M plus minus. So M plus minus is equal to M plus, that's 0.300, raised to the N plus, which was, that should be N plus, which was 3. M minus was 0.100 raised to the first power, and this whole thing is taken to 1 over N plus minus, which is 4, 1/4. We put that in our calculators, and what did I get? 0.228. So this is, if you want, an average concentration of ions, considering both the sodium ions and the phosphate ions. This is molal. All right, the activity coefficient, we're going to estimate these, of 0.3 molal solution of sodium is about 0.8. The activity coefficient of PO4 is around 0.1. So what's the mean activity coefficient? All right, so the mean activity coefficient, gamma plus minus, is the activity coefficient of the plus species raised to the N plus power. The activity coefficient of the minus species raised to the N minus power, and all this is raised to the 1 over N plus minus power. All right, the problem gives the, for the plus, the activity coefficient is 0.8. Okay, so that's 0.8. Sodium has to be raised to the third power. That's what N plus is. Phosphate, the activity coefficient there is about 0.1. That's raised to the first power, and this is the 1 over 4th root, and this comes out to be 0.476. So the activity of the plus is 0.8, the minus is 0.1, and so the average activity coefficient of considering both species is 0.476. And finally, let's calculate the mean activity. The mean activity was A plus minus. That was equal to gamma plus minus, which we calculated, molality plus minus, divided by M0, raised to the N plus minus. Gamma plus minus, 0.476. Average molality, 0.228. Our standard solution, or our standard state concentration is 1 molal. This is molal. This is molal. Activity coefficients don't have units. And this whole thing is raised to the 4th power. So the activity is 1.39 times 10 to the minus 4th. Whoa, that is low. A low concentration, or low activity. We have like a 0.1 molar solution of this, and we'd expect, the activity to be around there, at least not too far down. But in fact, for those ions in solution, the average activity is 10 to the minus 4th. So wow, they're not very active. They must have a lot of interactions between themselves and with the water, as you expect for a charged species. All right, so that's it. For the next part of this lecture, we'll talk about ionic strength, the energy of formation of ions, and measurement of activity coefficients. And in Lecture 14c, we'll talk about calculation of activity coefficients, and that will be it for equilibrium thermodynamics.